All right, with this problem, let's first look at an example. So we're dealing with Pn in this problem. So we'll look at P5, the path graph on 5 vertices. Now before we even work on this problem, the thing I'd like you to notice is that there's only 2 possible answers for this problem. The answers are either 1 or 2. And that's because in a path graph, there's only 2 possible degrees for every vertex. Either you have the endpoints that have degree 1, or you have the other vertices which have degree 2. So that's it. The only possible answers we could get for this problem are 1 or 2. Now the major assumption of this problem is that n minus 1 is the smallest positive integer such that a to the n minus 1 ij is not 0. And the smallest positive integer part, that's really important. So I circled it there. In our example graph here, P5, n equals 5, and so n minus 1 is 4. So what that means is that, so what this right here means, this whole thing, is that the ij entry of a to the 4th is not 0. And 4 is the smallest positive integer for which that's true. So because 4 is the smallest, smaller ones, that can't be true. So that means a cubed ij has to be 0. A squared ij has to be 0. A to the 1st ij has to be 0. And remember what these numbers count. These numbers a to the power ij. They count the number of walks of length that power from vi to vj. So this one is the number of 4 edge walks from vi to vj. This is the number of 3 edge walks from vi to vj. This is the number of 2 edge walks from vi to vj. This is the number of 1 edge walks from vi to vj. Remember, a 1 edge walk is just an edge. All right. And so think about why this has to be equal to 0 here, right? Because this is the smallest positive integer such that we have not 0. So if it's the smallest one where we have not 0, we can't have this one not 0 because then that would be the smallest, right? And that doesn't make sense. So our assumption is that 4 is the smallest for this example here. All right, so now look at our graph here. Let's say that, let's say for sake of argument that vi is that vertex and vj is that vertex. Is that possible? And the answer is no, it's not possible, right? Because if that was the case, then we would have a 1 edge walk from vi to vj. And so then this would not be 0. Okay? So is it possible now for this to be vj? And the answer again is no, it's not, right? Because then that would be a 1 2-edge walk from vi to vj, and that number would not be 0. Is it possible that that's vi and that's Vj. And again, no, it's not, right? Because then we'd have a 1, 2, 3 edge walk from Vi to Vj, and that would not be 0. So if all of these are 0, this one, and this one is 0, and this one is not, then it must be the case that we have Vj there to get a 1, 2, 3, 4 edge walk. And so that forces Vj to be an endpoint, and so the degree of Vj is 1. Now generalizing this idea to, let's now generalize to Pn. So Pn, and we're told that a to the n minus 1 ij is not 0. And that's the smallest. So remember that Pn has n minus 1 edges. This we saw in the Graph Theory 1 worksheet. So could it be the case that Vi is here and Vj is there? And the answer is no, right? Because Pn has n minus 1 edges, so we need so there's n minus 1 edges in all of Pn. N minus 1 edges from one endpoint to the next. So if Vi and Vj are not endpoints, then a to the smaller than n minus 1 is not 0. But that's the smallest. It's got to be the smallest. So this can't happen. So then maybe Vi is there. But still, if this is the case, right, then we have something like a to the n minus 2 ij is not 0. But again, this is the smallest. So this can't happen. And this forces Vj to be an endpoint. And so the degree of Vj is 1. Our answer is 1.